Hi everyone, today I'm very happy to present our work, V-JEPA, Revisiting Feature Prediction for Learning Visual Representations from Video. Some studies have shown that children can acquire new concepts by just watching one example. So if you show them these weird objects on the left and you show them later in the later tests, they will be able to recognize them. There is also a study that shows that children acquire visual capabilities throughout their development, such as face tracking, object permanence, or gravity. So the capacity for humans to become proficient at some tasks builds on their prior knowledge that they potentially acquire by passively observing the world. So how to learn by passively observing the world? This is what self-supervised learning tries to do. In self-supervised learning, you mask an input and you train a network to predict this missing part. This is how LLMs work. With LLMs, you mask a word in a sentence and you train the network to predict the missing word. But this works really well for text, but it's harder for perceptual inputs because text is discrete and visual inputs are not, and text is also more semantic. So how to effectively leverage self-supervised learning pre-training for non-textual inputs and potentially for video, this is what we are going to tackle in this work. We'll focus on the JEPA architecture, so joint embedding predictive architecture, that differs from generative model in the sense that all predictions are done in an abstract representation space. So starting from some data from any modality, the principle is the same. You mask the input, feed that to an encoder, then to a decoder or predictor, and perform the prediction. So we introduced V-JEPA, a video joint embedding predictive architecture. With V-JEPA, we sample a video clip, and then we mask this clip using random tube masking. These masks can be obtained by sampling blocks of various size. Then, once we have a masked version and an unmasked version, in practice, we use transformers with visual transformers with patches. So we remove the masked patches, and we concatenate mask tokens, which constitute the input of the predictor, and use the mask tokens as the predictions that we match to a target that is unmasked. Here is our experimental setup. We pre-train V-JEPA on large datasets of large academic datasets of video, such as kinetics or something, and how to 100 millions. And then we evaluate this model on a set of downstream tasks, such as action recognition, action detection, and image classification. We use the something V2 datasets as our main metric that we track because it is a very motion-based dataset. Here are the results. We measure the performance on something V2 and on kinetics. And first, we have a cluster of methods, the triangle cluster, that perform best on appearance-based task, the appearance-based task, so kinetics. Then we have with square models that perform well on temporal-based tasks, something V2. And we see that the triangle cluster is mostly composed of image-based model, and the square cluster is mostly composed of video models. And finally, we have V-JEPA that leads to strong off-the-shelf performance for both the appearance-based task and the temporal understanding task.